Hello everyone, my name is LIAN. Today, I'm here to present my research on thermodynamic analysis of fuel oil blended stock, FOBs, to light hydrocarbon. Liquid oil will still be responsible for 28% of the world's energy supply by 2025. Due to the depletion of fossil fuels, we are looking for low-cost alternatives capable of meeting global energy demand. Thus, fuel oil blended stock, FOBs, was proposed as an alternative fuel stock in this study. So, why was FOBs chosen? This is because FOBs is an undesired product from the petrochemical refineries and it is very difficult to further process. The direct usage of FOBs lead to environmental, financial, storage, and treatment problems. Heavy fuel oil, HFO, was an example of FOBs. Due to the high percentage of saturates in HFO, N-ecosane, C20, was chosen to represent HFO, which means to represent FOBs in this study. Due to the limitation of FOBs, oxidative cracking was chosen to upgrade FOBs because it allowed the use of low-cost reactant with low emissions of pollutants compared to conventional cracking. This approach not only offers a modern way to dispose of the FOBs in a sustainable manner, but also acts as a solution for the scarcity of natural oil and gas. Thus, we have outlined the problem statement. Due to the limitation of FOBs, it is necessary to transform them into light hydrocarbons with higher economic value. Currently, limited research was conducted to investigate the cracking of FOBs with oxygen. Besides, there's no similar research on oxidative cracking of FOBs that use N-ecosane as the model compound. Moving on to the objective of this study, firstly, to determine the reactions that occur during the conversions of FOBs into light hydrocarbon. Secondly, to investigate the major products formed during the conversion of FOBs. And thirdly, to investigate the effects of reaction parameters of different temperature, pressure, and ecosane to oxygen molar ratios, EO, on the compositions of product in equilibrium. Thermodynamic analysis was applied to investigate the possibility of oxidative cracking of N-ecosane model compound. The overall methodology was shown, including the determinations of possible reactions and products, the characterizations of reactions, parameter study, followed by thermodynamic analysis and calculation, and finally was the analysis of the result. HSC chemistry software was used to perform thermodynamic analysis based on total Gibbs free energy minimization method. A mixture of ideal gas was assumed, where carbon was the only solid. Reaction kinetics, reactor designs, and operation were neglected in this study. Moving on to result and discussion. The main reaction that occurred was oxidative cracking of N-ecosane with oxygen. It was exothermic and spontaneous reactions. Besides, other side reactions such as partial oxidation, methylation, reductions of CO and CO2 also occurred. After the main reactions, the first products as shown in the overall reaction network undergoes secondary reactions until equilibrium was achieved. Hydrogen and methane were the main products formed in this study. Next, the effects of temperature and EO on product yield at 1 bar were analyzed. For hydrogen production, the yield of hydrogen produced increased with the increase in the reaction temperature. The optimum condition for hydrogen production was achieved at EO 0.95 to 0.05 at 1273 Kelvin. The rapid increase in hydrogen synthesis in the early stage was mainly contributed by cracking and partial oxidations of N-ecosane. On the other hand, methane yield was higher at lower temperatures and it decreased gradually with the increase in the reaction temperature. Similar to carbon formation, more methane was produced in a higher yield due to the presence of more carbon in the reactant. Methane production was optimum at 573 Kelvin. Furthermore, the effects of temperature and pressure on product yield at optimum EO was analyzed using contour plots. The optimum hydrogen yield was recorded at higher temperatures and lower pressures, while methane generation was more favorable at lower temperatures and greater pressures. To conclude, the main products formed were hydrogen and methane. The optimum EO was EO 0.95 to 0.05 at 1 bar. The suggested atmospheric pressure condition is safer than high pressure condition. The oxidative cracking process seems to be beneficial as only small modifications are needed to supply oxygen stream into the reactor. And that's all from me. Thank you for listening.